So assalamu alaikum. So welcome to lecture number 3 after mid-semester exam. So in this lecture we will cover the topic transformer tap changers. So what is actually transformer tap changers? So if we look at the construction of the transformers, here you can see that this is a power transformer. So in this power transformer, the main components we have two windings. One is a low voltage winding and the other is a high voltage winding. On the top of the transformers, if you look at the top of the transformers, let me open the laser pointer. So here you can see the bushing. So this is where the high voltage terminals are connected. Actually, if you look at the transformers, you can notice that in one part they have a higher insulation. So by these discs, each discs you mean that the insulation level is higher. That means that this terminal should be the high voltage terminal. The other terminals is here in 6. So this 6 is the low voltage terminal, because here you see that the insulation given here is lower. So first the energy, the electrical energy, the source is connected to either of these low voltage or the high voltage terminal, depending on whether it's a step down or step up transformer, but the voltage level is linked with this insulation level, as you can see from this from this chocolate color insulator discs. These insulator discs can be of ceramic insulator, it can be of epoxy insulators, it can be varied, but this particular thing that allows the current to go in or out of the transformer is called bushing, bushing. So this from the visual you can see that this is the high voltage terminal, this is the low voltage terminal, and we have a conservatory tank here, and this is a oil cooled transformer. That means inside the transformer it is filled with oil, and then you have a high voltage winding and a low voltage winding, which is mounted on the core. So surrounding the core you have normally a concentric high voltage and low voltage windings are placed. Now, what is actually the transformer tap changers? So we know from the voltage conversions of the transformer that the voltage turns it will be, whether it's a step up or step down transformer, the voltage conversion will be linked with the number of the turns. That means that if it is a if you have a let's say the primary voltage Vp and you have the secondary voltage Vs, this is linked with the number of turns, this is Np, so the number of turns in the primary divided by the number of turns in the secondary, so it is linked with the number of turns. So normally without the tap changers, the transformers has a fixed turns ratio. That means that each particular transformer can transform with a fixed ratio. For example, we may have a transformer with 11 kilovolt to 66 kilovolt, for instance. So it may have a fixed transformer turns ratio. But in power system, if you recall that depending on the load, you may have some voltage drop over the line, and at the end of the line you may have a situation where the voltage is actually much below than the ideal voltage level that it should have. For example, if you have a distribution line, so let's say this is our 11 kilovolt bus, and then from here you have a distribution line, maybe here you have a transformer connected here, and from this 11 kilovolt this transformer actually transforms it to 400 volt line to line volt or 230 volt phase to ground volt. So this is a three-phase line. So this is a three-phase line, and of course it has another neutral. So your home may have a so this may be your home, so it may be connected to a phase and a neutral connection, or if it is a higher load, it may happen that you have three-phase connections. So three-phase connections like this, and of course it is also connected to the neutral. So what happens is that if you have a lot of loads connected here, that means that you will have a lot of current that will flow through this line. So in this line you will have a higher current will flow if you have a lot of loads connected. Now this higher amount of current will also, because of the line impedance, it will drop a significant amount of voltages over the load. That means at the end of the line, the home which is connected at the end of the line may not experience exactly 400 volt line to line voltage. It may have a voltage which is lower than much lower than 400 volt. In the grid code, it is normally plus minus 10% of the nominal voltage is allowed to have. For instance, if it is written 400 volt line to line voltage, that means you are allowed to have minus 10% of it, which means that if the voltage here is less than 360 volt, that means you are violating the grid code, and in that cases you should have certain mechanisms so that your voltage is not 360 degree, rather it is higher than 360 degree. And one of the way to overcome this issue with the voltage is to have a variable turns ratio. So instead of having a fixed 11 kilovolt to 400 volt transformer, if you have a turns ratio in the secondary which can be increased when the load is high, then you can eventually, instead of 400 volt, maybe you can here have 420 volt, and in that cases maybe at the end of the terminal, at the end of the line, the voltage you will for the cases when you had a fixed trans ratio, then maybe you do not have the control on the voltage at the end of the line, but now with the help of this variable turns ratio, it is possible to have a control over the voltage. Now this particular task is done in the transformer using the tap changers. So the term tap changers means that in the secondary you have a winding. Normally you have a winding, and the tap changers means that you have a tap that you can attach to the winding. So by changing this tap at different locations, you can eventually control the number of turns. That means that you can eventually control the output voltage. So this is particularly called tap changers. And on-load tap changers mean that there are two kinds of tap changers. One can be on-load and other can be off-load. On-load means that you can change these tap settings when the load is connected. So while on-load condition, when the load is connected, you can control these tap changers. Now one important thing to add here is that this allows flexibility in the operation of the transformers, because you can control the output voltage with the cost of the lifetime of the transformers, because tap changers, in contrast to fixed turns ratios transformer where you cannot change the number of windings, in tap changers, once you switch from one tap to the other tap settings, you have a small arcing every time you change it. You have a small arcing there, and because of that this is actually a vulnerable part of the transformer that degrades first. So the transformers with the transformer tap changers is not necessarily always the good one in terms of the reliability, but it is helpful in terms of the operation. Okay, so so this is example. For example, this is a variac. this is an example of a tap changer. So in the Variac we actually rotate this knob at different tap settings, and by doing so we actually control the output voltage. So you have seen this Variac in your laboratory. So you have seen that you have a certain input voltage, and by rotating this knob you can actually control the output voltage. So what you actually do here is that you control the taps here. So by connecting with different settings, you actually control the number of turns, and eventually you control the output voltage. Okay, so instead of mechanically rotating switch like this can be controlled also by the use of thyristors, by using this as a static switch, as it's shown in the figure here. So in the primary we have this primary winding, and in the secondary you have this tap changers here. So in this particular example we have two different tap settings. One is here and the other is connected to here, and we have two thyristors placed in anti-parallel direction, and depending on our need we may connect this part, or we may connect this part, or we may connect both of this, depending on the scenario. So you will see it. Okay, so when we are only connecting this terminal, and when this is off, that means the output is having a voltage of V1 only, which is of course less than the maximum amount of output voltage that this transformer can generate. These transformers can have at maximum when this part is connected, T1 is connected and T2 is connected. At that time the output voltage is V1 plus V2. In contrast, if we only allow T3 and T4 to conduct, at that time you can have a output voltage of V1. So here V1 is root 2 V1 sine of omega t, and V2 is root 2 V2 sine of omega t. Okay, so as I said that depending on the controlling of this thyristor, we can have a output voltage that is ranging from 0 to V1, or we can have output voltage that varies from 0 to V1 plus V2, or we may have an output that varies from V1 until V1 plus V2. So the first one is the most simple case. In this particular case we are having the control range of the output from 0 to V1, and what we do is that we simply do not connect this part. So we do not give any trigger signal in the T1 and T2. Instead we only allow T3 and T4 to conduct. So when for the positive half cycle T3 will conduct, so for the positive half cycle current will flow through this, and for the negative half cycle the polarity is reversed and the current will flow the other way through this. So our output voltage is of course depending on alpha. So if alpha is the firing angle, so the output voltage will look like this, and this is our V1. So this is our V1 voltage, and by having a variable alpha you can control the output voltage here. So the output will vary from 0 to V1. When alpha is 180 degree, then the output is 0. When the alpha is 0 degree, at that time the output is V1, and when alpha is in between, you will have output voltage in between. Okay, so in the control range 2 we can vary the output from 0 to V1 plus V2. In this arrangement we turn off these settings, and instead we turn on T1 and T2, and that means that for the positive half cycle T1 will conduct, so it will conduct like this, and for negative half cycle T2 will conduct. So the output voltage will be V1 plus V2, and this is the maximum of it is root 2 V1 plus V2 here. And by controlling the alpha, you can eventually control the output voltage in the range of 0 to V1 plus V2. Now this range is actually also covering the range from V1 to V1 plus V2. If you look at it here, the control range 2 is from 0 to V1 plus V2, and control range 3 is from V1 to V1 plus V2. That means that this part can also be done by only controlling at different firing angle, this alpha. However, if you have a different tap settings, then you can take advantage of both of these thyristors, both of these two branches here. So thyristor T3 is turned on at omega t is equals to 0. So T3 is turned on, so this part is turned on from 0, so this is on. So from 0 this is on until alpha. So at alpha T1 is triggered. So at alpha, when T1 is triggered, at that time T3 ceases to conduct, and T1 actually the current starts flowing through T1, because when T1 is triggered, this is turned on. So the voltage here, voltage at this terminal is actually this potential is the same as this potential, and that makes this thyristor reversed biased. As a result, this T3 is turned off. So you have current flowing through T1 after alpha. So from alpha, the output voltage is V1 plus V2, whereas before alpha, from 0 to alpha, this is the same as the V1. This is the same as the V1. So the root 2 is the big value here. So this is V1, and then this is actually following V1 plus V2 until pi, and from pi plus alpha this is 0. No, this is not 0, this is actually the same as V1 again. So in the opposite direction you trigger T4, and then after pi plus alpha you trigger T2. So and this is how you can actually get a voltage in the range of V1 until V1 plus V2. Now what's the benefit of this circuit in comparison to this operation is that in this particular operation, if you notice here, then we can see that there is a very high rate of change of voltage here, which is changing very fast, which will actually add a lot of harmonics in comparison to this kind of operation. So here you see that this is not as high as in the previous cases, because previously it was actually following V1. Now instead of 2 branches, if you add more branches, then you will eventually achieve much smoother operations if you need to control the output voltage. So this operation actually reduces the harmonic content. Okay, so basically that's it. You can derive, once you know the wave shape, you can derive the RMS and the average voltage if you need to calculate it. Now if I recap the whole thing, then the transformer tap changers is actually changing the tap position of the transformer so that you can control the output voltage, and you can do that manually. That means using mechanical switches. It has actually 2 types of tap changers. One is the on-load and the other is the off-load tap changers. Off-load tap changers is the one that you have to disconnect the load first, and then you have to mechanically go there, physically go there and mechanically change the tap settings. So if you look at the transformers here, so you have to turn the load off, no current is flowing through here, and then physically go there and then change the tap settings. There is no normally in the transformer there is a within this box you have a like a wheel arrangement where you have to rotate this wheel to change the transformer tap settings. That is what is done using in off-load arrangement. In on-load arrangement, you can do that when the transformer is connected. You can do that mechanically, or you can do it remotely. So if you want to do it remotely without mechanical involvement, then you can do that by using thyristor arrangement like this. So the benefit of using thyristors is that you can control in a mechanical settings. You cannot control the output voltage by changing alpha, whereas using a thyristor, first of all you can precisely control the output voltage, and secondly you don't have to physically go there. You can just give a trigger signal in the thyristor, and that will start the operation. So that is it for this lecture.